So in this video I'm going to talk about inductors and inductance, and this is covered in chapter 33.1 of the textbook. Alright, so first off, what exactly is an inductor? Well, if you imagine you have a solenoid, right, so just some coils of wire, and you put that in a circuit, so you hook it up into with a battery or power supply of some sort. And if there's a non-zero current, well, there's going to be a current in the solenoid, which means it's going to generate a magnetic field. So you can think about the solenoid as storing the magnetic flux and the magnetic field energy. And this is actually known as an inductor. So an inductor, usually the way you think of an inductor as an ideal solenoid, so just a coil of wire. So the magnetic flux through an inductor is proportional to the current. So phi here is just the total magnetic flux, I is the current through the coil, and L is the constant constant of proportionality, and it's known as the inductance, or technically it's the self-inductance. So the units, well, it's flux over current, so Webers over amps, or Tesla meters squared per amp, and that's known as a Henry, and it's abbreviated capital H. So the SI unit for inductance is the Henry. So, and you can also work out what the energy stored in the magnetic field of an inductor is. So the potential energy is 1/2 times the inductance times the current squared. And of course, for an ideal solenoid, well, we know what the field in an ideal solenoid is, so we can actually work this out, and the inductance is mu naught n squared times L times A, where little n is the number of coils per length, and L is the length. Or you could write it in terms of capital N, which is the total number of coils. So it's mu naught over capital N squared over the length of the solenoid times the cross-sectional area A. Alright, so what happens then? So let's say we have an inductor. We put it in a current, and the current changes. So imagine we have a variable DC power supply. So the circuit symbol for that, well, it looks like the DC power supply or the battery, but the little arrow here means that it's variable. So if the current in a circuit with an inductor changes, well, remember there's some magnetic flux in the inductor, and if that flux changes, Faraday's law of induction says that we're going to induce an EMF. So, and that's known as the back EMF because, well, Lenz's law says that the induced EMF and the induced current has to oppose the change. So that's why where we get the term back EMF. So for example, on the little picture on the left here, so imagine the current is increasing. So your little variable power supply, you've got a knob and you're increasing the current. Well, if the current is increasing, then the flux is increasing. So the induced EMF has to oppose that. So you're going to get an induced EMF opposite to the applied EMF. Or if you go the other way, so now imagine we've got our variable power supply, only now we're turning down the current. So the current is decreasing. Well, if the current is decreasing, then the flux through the inductor must be decreasing. So the induced EMF has to oppose that. So you're going to get an induced EMF in the same direction as the applied EMF in order to try and keep the flux constant. So now we can define an inductor rule. So to find the potential difference across an inductor in a circuit, well, if the current isn't changing, the inductor looks just like a wire, so there isn't any potential difference. So if the rate of change of the current, di dt, is 0, then the potential difference across the inductor is going to be 0. If the current is changing, well, the EMF, the potential difference is going to depend on how fast the current is changing. So there's a negative sign from Lenz's law, the self-inductance L times the rate of change of the current. So, and you can, as an aside, so and the book does this, you can actually use this to derive the transformer equation we talked about last chapter. And again, well, assuming that the flux is identical in your primary and secondary coils, and remember the transformer equation says that the potential difference across the secondary coil divided by the potential difference across the primary coil is equal to the number of turns in the secondary coil divided by the number of turns in the primary coil.